好的，这边听得见吗？应该，那我开始了。好像有人在讲话，听不见。怎么播放？
退出。就是这个，好，对。
好，那我开始了。So today I want to talk about the quasinormal walls and cosmic ER/EPR in the city. And I'm Hoiki Liu from the University of Tokyo, and thanks for inviting me for this conference. And this talk is also based on my PhD thesis, also based on an upcoming paper, which we are still working on it, but hopefully we can publish it during January. So basically, our main motivation is about yes, for the further understanding of DSCFT as a way to explore the UV complete theory of quantum gravity, and which DSCFT is basically a kind of holographic principle, which it suggests that a bulk theory with quantum gravity is equal to its lower dimensional boundary theory without gravity. And one of the rather well-studied one is ADS-CFT, which like compared to DSCFT, but as we know, our actual universe is not entirely static space, but like our past, the history of the universe and also the future is more relevant to the static space. So therefore, it is it is important to study DS or like quantum gravity in DS for practical uses. So that's basically our main motivation. And the reason that we study global, like the static space in global coordinates compared to the more usually studied one, which is the flat slicing, is because it's more relevant to our second topic, the ER/EPR statement, and which it's this statement suggests that the emergence of the bulk spacetime geometry can be seen from the structure of quantum entanglement. And one famous example would be like two widely separated and pair created black holes in a pure state, and in where like there exists two entangled states in which I will explain a little bit more details later, but it's basically like two entangled states in each asymptotic region of a black hole. It's called the Einstein-Podolsky-Rosen pair, which in short is EPR pair, and they are equivalent to the ER bridge, the Einstein-Rosen bridge, which connects the two asymptotic area in the black holes. So that's basically the statement. And this ER/EPR statement is well understood in the concept of ADS-CFT. But as we will see later, the static space has a similar structure as the eternal black hole. So it is considered reasonable to think about the DS-CFT version for EPR. And actually, the team combined by Kotter and Strominger has been they studied about this for the DS-CFT version in this February. but only for light scalar fields. And in their paper, they showed that the Euclidean vacuum for global ds can only be expressed in the boundary representation as an entangled and pure thermal double field state. And entire ds universe can emerge from constant entanglement between two boundary safeties. And also they suggest that the required entanglement produce the ER bridge, which completes the bulk due to a global ds. So that's so far the conclusion they made. And so which follows to our work is basically kind of basically based on their work, but we extend these following discussions to heavy scalar fields, which is like scalar field much less studied in the context of the SCFT, because the behavior of heavy scalar field is rather complicated than the light scalar fields. But as I said, if our ultimate goal is to study about the UV complete theory, because the theory contains all the mass spectrum of the particles. Therefore, we need to study. We doesn't only need to study light field, but only heavy field as well. So it is important to extend this. So basically, our result of our work is the first one is that we managed to produce the thermal field double state description for heavy scalar field as well. And also most of the results for the light scalar fields that this previous work that they derived applies to. However, there are also some differences between light field and scalar and light field and heavy fields, which is well, because of the rather complicated structure or behaviors of heavy scalar fields. It is more obscure to identify the boundary theory with a CFT. But they do have some similarities that suggest that they could be identified probably with a CFT eventually. So basically the outline of this talk is like this following. And so we have done the introduction already. Then next I will give a brief review about the eternal black holes and ER as a background. And then as the first part, I will briefly review the work of Kotler and Strominger for light scalar fields. And for this first part is it's about our work, which we attend this discussion to heavy scalar fields. And at last, I will do a brief summary about this work. So first of all, an eternal black hole in ADS is basically maximally extended ADS Schwarzschild spacetime, and its Penrose diagram is given by here, and which we can see it have like two asymptotic boundary, and so which one is the future boundary, well, future infinity and past infinity, and also there are two asymptotic regions which we denote here by left and right, and each of them has a boundary, which we write it like boundary 1 and 2 here. So because of this double boundary systems, it means that if you consider the CFT, it means that it deals to two copies of CFT. And so how does this geometry relate to thermofield double systems? So first of all, this thermofield double homomorphism is a method to treat the thermal and mixed state as a pure state in the bigger systems. So for example, if we consider any kind of QFT with a Hamiltonian edge and also a complete set of eigenstates, which we denote the eigenvalue by EM, it can be written as here. Then if we double the degree of the freedom, like consider another QFT, which is consider new QFT, which is two couples of the original QFT, which like by using this N, we can write two states in terms of their product. And so using this kind of double copy state, we can consider the thermofield double state, which is defined by here. And we can see it's a linear combination of a product state and also weighted by a kind of thermal factor. So with this state, we can decide the density metric of it. It's given, the definition is given by here. And if we trace over, for example, the second system, we obtain the reduced density metric for the first systems. And then we see that the density metric is in the form of a thermal density metric. And like beta is the inverse of the temperature. So this result means that if we restrict our attention to system 1, then this pure state in the double system is indistinguishable from a thermal state. So this is how the thermofield double formalism, like treating a mixed state as it's like a purifying a thermal mixed state procedure. So we're not going, because the limitation of time, we are not going to deduce how like the eternal black hole is related to TFT, but it's known that it is due to the DFT states. And let's look at this Penrose diagrams. Like the left side of it is due to a CFT1, CFT2, and the right side is due to a CFT1. And meanwhile, there exists an Einstein-Rosen bridge connecting these two sides, and they are created by entangling the CFT1 and CFT2. So for example, if we put like one operator in the left side and one in the right side, because these two systems, they are not coupled with each other. So in that sense, they are, for example, we consider this kind of correlation function, then this two operators, their correlation function should vanish, although because they are entangled, so therefore their result is actually non-zero. And this can also be explained by the existence of this Einstein-Rosen bridge. So this is basically the EPR statement for eternal black hole in ADS. And next, let's go back to the theta space. So if we look at the Penrose diagram for the theta space, we can see that it's pretty similar to the eternal black hole ADS. Although of course there are some differences. For example, they don't have this singularity around the boundary, around the future and past infinity, and also so this two patch is called the static patch for the theta space, and for here they don't, unlike eternal black hole ADS, they do not have a boundary, but instead they just have a north pole and south pole. But nevertheless, they have some similarity of the Penrose diagrams. So it is reasonable to consider the DSFT version for EPR. And so for more details, usually when we consider global deceders, we think about Hilbert space. Usually they are built on the global S3 slice, like this kind of slice. And so for this slice, we know that there are also geodesically complete topologically like R3 spacelike slice, which ends on like one point on the future or past boundary, and so we are consider like the 4-dimensional theta space. So in that case, each point on the future boundary is S2 sphere. So there exists, like for example, we start from here and draw a line, like a space-like line, and it's on north poles, and there must exist a geodesically complete topological slice. And in some early work from Sasaki, Tanaka, and Yamamoto, they this studies that at least there exists this kind of hyperbolic slice, which satisfy this kind of the conditions. And on the other hand, if we start from an arbitrary point at these like S2 point on the future boundary, it's not we of course we can draw a line which ends on the North Pole, but also we can draw a line on the other from the other side which end on the South Pole. So which means that this every S2 on the boundary, it's also a boundary of a northern slice, northern R3 line, and also a southern R3 lines. And these two R3 slices, their topological sum reproduce the S3 slice. And this is kind of similar to the double copy like prescription for the CFT case. Wait. And also this is like an analogy of the left and right Ringler wedge to that of the global Minkowski space. So this is the background of the extension for EREPR statement for DS safety. And next, I will briefly review what the previous research studied about the light scalar field, which is the simpler version of it. So to study it, oh yes.
Einstein Rosen bridge. Can you, for example, reconstruct?
Yes, I think so. So basically, the suggestion of the statement of is the geometry, including the metric, is formed like it's emerged from the entanglement of these two states. So I'm not sure about any like concrete examples. So, but yeah, I think it's in principle possible to reconstruct the metric. So okay. So to study global safety, here we used, or they used, the quasinormal mode basis, which are there are kind of mode bases that like the kind of modes that they decay over time, and also purely outgoing toward the horizons. And although they are compared to global space, global coordinates, they are often studied in static coordinates. And so this kind of basis, they're kind of problematic because they are with complex energy values, and also they have some unitarity issues. But nevertheless, it presents as a promising basis for considering the safety because of its asymptotic behavior around boundaries. So let's introduce what kind of modes there are. So in order to do that, we consider S4 global coordinate, which is given by here, and this part is just the angular part. And here we denote the North Pole at phi equal pi and South Pole at psi equals 0. And the massive scalar with a wave equation is given by here. And for this wave equation, it has a highest and lowest weight representation of the DSSO for one isometric group, and they are given by this phi plus minus qn and plus minus aqn here. And by the way, here the large delta plus minus is the conformal weight, and it's given in terms of the mass of the particle. And so for light scalar field, it means that n square is lower than like d squared over 4. So which means this delta is a real number. And for heavy scalar, because this part becomes purely imaginary, then the delta becomes a complex number. So that's the biggest difference between, or the origin between light field and heavy scalar field. And so these two solutions, they are corresponds to the quasinormal field and also anti-quasinormal field for the northern static patch observers. So the reason that they are the highest and lowest weight solution is that they are, so in terms of the scaling vector, there exists like this kind of scaling vectors, which they are combined with the dilatation and also free rotational scaling vectors and 6 boost scaling vectors. And this the quasinormal mode and anti-quasinormal mode, they are actually eigenfunction of these dilatation operators, and their eigenvalue are given by like plus minus delta. And also the dilatation operator, it can also be written as partial t, which this large t is the static patch time. So it means that the static patch Hamiltonian can be written in as like I times L0. So L0 itself is related to the energy of or Hamiltonian of static patch. And also the highest and lowest weight conditions as given by here, which if we act m minus k to plus minus qn, or m plus k to aqn, then it becomes 0. That's the meaning of the highest and lowest weight. So which means if we are able to obtain the descendants, also the ascendants of this highest and lowest weight functions, which here we denoted by a single letter b here, which is a collective indice, and it just denotes how many like this m case we act on the primary fields. So therefore, from all of those setup, we can be obtained in totally 8 set of highest weight representation, which is given by here. Although it's proved in Cotton and Strominger's paper that they are actually over complete spaces. So actually, we don't really need all the 8 of them to reproduce for example, green functions in Euclidean vacuum. We only need 4 sets of them. So here for light fields, we decide to only use the one who has the plus sign, like this plus qn and plus aqn, and also their complex conjugate. And then, so that's basically the construction for light field for quasinormal modes. So, but instead of just using the modes themselves, we use another like construction or combination for light scalar fields, which they only covers the half of the zeta space. And so here we defined 4 set of modes here, which we denoted them by phi, fn, fs, mpn, and mps. And those letters are like they stand for each region of the global zeta space, like as this. For example, the N stands for north, and S for south, and F for future, and P just for past. So if we look at the explicit form of this function, we can see that. So for example, phi fn, this function only has value in the upper triangle of the global de Sitter space. And if we go to the lower part, the value of the function will vanish and we will just obtain a 0. So that's, and also the same applies for the rat-free functions. So we are going to use this four-set function to construct the semi-double states and also the vacuum state. Before we proceed, we should note that this kind of construction for dividing fields into only covering half of the space, like this kind of construction is only possible for non-integer conformal weights. And for if the conformal weights are integer, then the function, there will be singularities appear in the function. So it is to be ambiguous how to treat it. And also they are like complete set of manifestly real modes. And next, after we obtain the full set of the mole, we are able to calculate the Klein-Gordon inner product of it, which the definition is written here, and we do the integration on the global free slice. And so actually the only non-zero ones are given by, they are only given by the products between Fs, Ps, or Fn and Pn, which means that if we watch this graph on pair slice, it means that only the modes share the same static patch have non-zero inner product. So if even for modes that share the same F or same P patch, their inner product will become 0 if they don't share the same static patch. That's one of the important property of this kind of construction. So after we obtain its Klein-Gordon inner product, we are able to define a bulk field operator, which we written as here. And here the function here, the function with this position indice, the variables, they're just function we introduced here. But those things with the hats, we denote it as operators. And this is similar to a bulk reconstruction formula. And here, by using the Klein-Gordon inner products, we are able to define the hat operators as here. And using this, it's easily seen that the commutation relation between the operators are just the same as their Klein-Gordon inner products. And then we can consider a rental-like quasinormal vacuum state, which we have, because we have 4 kind of modes here. So first we can, so we have seen that modes between Fs and Fn, they commute with each other. So we can define a kind of F0F vacuum for the future, for the modes which cover the future path, and also another vacuum for the past patch. So we have 2 vacuum here. And actually, so we don't need to use this one now, but because as we said, these 2 kind of operators, they are commute with each other. So it means that this kind of 0F or 0P vacuum can be further decomposed into a further subspace. And so if we look at the this kind of commutation, and also the Fs and Ps, their commutation relationship and relation, then we can say that, so this kind of 0F and 0P vacuum, they resembles the 0 position and 0 momentum eigenstates. And and then they're able to be normalized to 1. So that's how we define the vacuum state for those modes. So then after we define those F and P vacuum for each mode, the next step for us is we want to deduce the relation of this vacuum state with the more familiar Euclidean vacuum. So in order to do that, so first we know that actually the quasinormal modes and also the anti-quasinormal modes are proportional to Euclidean modes. So therefore, they are also Euclidean modes themselves as well, which means if we add those quasinormal modes or anti-quasinormal modes operator to the Euclidean vacuum, then it will vanish as well. So based on that, we see that usually the alpha vacuum is defined by, it can be defined by here. And so here we can just treat this quasi-normal mode operator as the normal annihilation operator, and this plus Qn dagger is the creation operator. So we obtained this kind of relation, and so then if we because we have relation here between the Qn modes and also this Fn Ps kinds of modes, we can invert the relation and deduce and express the Qn modes in terms of these 4 modes. So if we substitute them into this relation, we can deduce, eventually we can deduce like the relation between the first 2 0F and 0P and the Euclidean vacuum we know. And here, because from this formula, we just need to take alpha star to minus infinity. And so the result is given by here, which is an exponential and exponential kind of relation. And here we, so here I write the H plus, but it's just delta plus. So we obtained this kind of relation between the 2 vacuum and the Euclidean vacuum. So eventually when Euclidean. Euclidean modes means the modes, the basis we used to we used to define the Euclidean vacuum. So the annihilation operator of Euclidean modes, if we add that to Euclidean vacuum, then it vanishes. Like it's just the basic Euclidean basics.
The solution triangle.
Yes. Sorry, a few.
The solution of triangle equation.
Oh, it's not the solution of it, but so it's basically the solution of the normal de Sitter space Gordon equation. So basically, I think you know that how they defined. So they have a set of solution of this kind of the Klein-Gordon equation. Then one solution that is non-singular when you analytically continue it to Euclidean de Sitter. So that's the definition of Euclidean modes for de Sitter. So that's the meaning of Euclidean mode here. Okay. So, yeah, so next, so eventually what we want to do, why we did this, we derived this kind of relation is that we want to see, like the property of the density matrix. So, so first we can define the density metric of the usual Euclidean vacuum. But before doing that, as we said, because the like Fn and Fs modes, they commute with each other, which means that we can decompose the vacuum to even smaller subspace. Therefore, we can write it as 0Fn and 0Fs. And also the same applies for the P modes. And this is a kind of analogy of Minkowski's vacuum as a linear thermofield double. So we use this kind of description for this Euclidean vacuum. I basically just substituted it into these two vacuums here. Then therefore we can write the density metric for the Euclidean vacuum as here, which, well, it's a quite complicated formula, but basically here we can write it in a kind of product of this Fn and Ps state, and also Fs and Ps states. And after we obtain here, if we trace over, for example, the 1,000 modes, we can obtain the northern density matrix as here, and which here is a product of Fn and Pn vacuum. But so the main focus is the weight here. So if we look at here, we can see that it's an exponential 2 pi I h plus, where we have seen that because the Pn operator, their eigenvalue is precisely h plus, I mean, in terms of L0, which we have seen a few slides before. So it means that we can write this part in terms of the L0 operator, and because the L0 operator, as we mentioned before, is related to the Hamiltonian in static patch as here, which is the Hamiltonian equal to IL0. So eventually, it means that we can write the northern density metric as, so it's proportional to exponential minus 2 pi and h static. So, and this is apparently like thermal density matrix. So, and we can see that it is quite similar to the formal the thermal double field states that we presented before. And so, which means this result means that the DS4 partition function is actually the CFT partition function at a certain temperature. Oh, because so I omit some step, but so for example, we can write this part as yes. So their relation are given by here, where we denote the static patch time as large T. It's given by this things in terms of the global coordinates. And L0 is, its definition is partial T. And because, yeah. It's, yeah. Yeah, yes, that's true. Yes. Yeah, okay. Yeah, so from this result, so as a brief summary of this result, so therefore, basically we saw that those bulk states, they are actually created by acting those powers of, for example, phi ps on the 0f vacuum. So we can create different kind of states formed by this procedure. And this is actually similar or equal to a power of CFT states, which they are constructed by acting with the powers of the operator O, which is CFT operator, and of its descendants. And besides of this, we noticed that there are also another tower, which is denoted by phi Pn. And combining by these two features, we can say that a state in the bulk Hilbert space is actually lies in the tensor product of two boundary Hilbert space. And so this is different from the usual ADS CFT in global SDS, for which the bulk and boundary Hilbert space are identified. But however, it matches with the description of the internal ADS black hole, which we just mentioned, as thermal field stable state in ADS CFT. So therefore, it corresponds to a kind of Yale boundary description. Therefore, so we have seen the similarity between the bulk DS and also the the CFT, the boundary CFTs. Therefore, we can consider a DS CFT description for it, where, so specifically, we consider two 3D CFTs with a vacuum state, which we denoted by 0, 3. Like 3 is just the dimension. And we make this following identifications, which we consider true CFT, and the first CFT is constructed by this Pn operator and also Fn operators. And the second one is constructed by the PS and also Fs operators. And we denote it in terms of this A, B, and CD buckets. And they're defined, for example, the A are defined by a kind of CFT operator O here. And they are CFT operators with certain conformal dimensions. And so as we have seen before, the holographic dual to the Euclidean vacuum can be written as here, which is the product of these two substates, and also weighted by a certain thermal factor. And this is precisely the definition of a thermal field stable state, and with an imaginary temperature here. So here, which we can say is that like a global DS can be described by these two entangled states, and also its dual state to the Euclidean vacuum as a thermal double state. And let me see. And also that the bulk Hilbert space of a global de Sitter is isomorphic to two copies of CFT, which can be written as a product of here. And also in terms of one single copies, because we have seen that one single copies of each state, they are constructed by modes that does not cover the other static patch, but only like one static patch, and for example, only the northern static patch. So it means that the bulk particles in the northern static patch can be written as CFT Fock space state created by the product of OA. So it means that like the Fock space of the static patch is included in the Hilbert space of the dual CFTs. So here is basically the conclusion, also the description for global DS CFT correspondence for the light scalar fields. That's the work and the result from Chongqing and Kotler's paper. And as the next part, I would like, so in our work, we extended those discussion of the result to higher scalar fields. So the differences, as I mentioned, for higher scalar fields is that their conformal ways are not real numbers anymore, but complex number, which means that, for example, we take the complex conjugate of this delta plus, it actually ends as delta minus instead of not delta plus. So which means that if we want to construct the same like FNPS mode only covers the half of the city space, what we need to do is, like, instead of phi plus Qn star, we need this phi minus Qn stars because of these complex conjugate relations. And also the same for other modes. So if we define modes as here, like the explicit expression of them are exactly the same with light scalar fields, and therefore they also they satisfy this kind of region covering conditions. But the difference is that now they are not real functions anymore, so they have their complex conjugate part. So in total, there are like six sets of functions we obtained. So before discuss, so yeah, that's the main difference between the heavy and light scalar fields. But also after regulation, we obtain their Klein-Gordon inner product, which has the similar behavior with the light scalar fields. As we can see, only the Fn and Pn stars or Fs and Ps stars, like the inner product between them, have non-zero values. That's basically the same property with the light scalar fields. Sorry. Although, as we have discussed before, in terms of the quasinormal modes or anti-quasinormal modes, like we have 8 towers of those modes, and actually only 4 towers of them are enough for forming and complete spaces. So, but instead we have in total like 8 modes, 8 towers of modes here. So it is possible that it's actually an over-complete spaces. So instead of using all these 8 modes, we construct kind of northern and southern modes by combining a part of those FNPS modes, as here, which like we pick one mode from include the future bound include the future patch, and one mode include the past patch, and also the same for the southern modes. And here, this exponential is just a phase factor where this theta n can be any values, but as we can see later as well, it actually can be absorbed as a part of the second term. So by field redefinition. So for simplicity, here we just set it to pi over 2. And so here we have this phi n and phi s mode plus their complex conjugate. So in total, 4 towers of mode. So we still need to check it, but because they match the numbers of the complete set of the quasinormal mode, it should be a complete set. And also, as we can see, their Klein-Gordon norms is given by here as well. Like only the modes between the northern modes and also between the southern modes are non-zero. Like, for example, phi n and phi s, they give 0 in the product. Therefore, we can say that it's a orthonormal set. And so, for example, the primary fields value is given by this function. So therefore, we can use these 4 sets of modes to construct a field operator. But in order to do that, we need to figure out like which modes, unlike, because it's a little bit different from the light scalar field, we need to decide which modes are the positive frequencies and which modes are the negative ones. So in order to do that, we can look in terms of the static patch time, T. So if we go back to the explicit form of those modes, we can see that, like, so for the primary parts, the plus minus Qm modes are given by this, like, exponential minus the, oh, sorry, I write H again, but it's actually delta. So minus delta T, and this one is just plus HT. So they are explicitly given by here. Therefore, we can say that in terms of the sign of this imaginary part, we can see that like phi plus Qn and phi minus AQn are the positive modes, and the remaining ones are the negative modes. So after seeing that, we are able to define the creation and annihilation operator as here, where the n are just some normalization numbers. This is pretty similar to the light field case, but with different mode functions. And the operators are just the same kind of definition by using the Euclidean inner product here. And we see that there are the operators commutator are also the same with their Euclidean inner product values. So after obtaining those operators, again, we are able to construct the vacuum for each of them. And here we denote it by N0 and 0n, also 0s, and just corresponding to the northern patch and the southern patch. But notice that because we have mixed the past and future modes when constructing those northern and southern modes, we are not able to separate the past and future modes anymore, unlike with the light fields. So this one is just like the vacuum already. We cannot decompose it to even smaller substates. And again, we want to derive the relation between those vacuum and with the Euclidean vacuum. We just repeat the same procedure. Like we can obtain a relation. We can write the Qm modes and also AQm modes in terms of this N and S modes, and just substituting it into the equation for the vacuum. Then we obtain the relation between for the Euclidean modes in terms of the product of this 0n and 0s modes. So we can see that it is also in the form of a Sommerfeld double state. So, okay. So similarly, we can define a density metric for the Euclidean mode, and it's given by here, which is pretty much the same form with the light field, but here we don't have the past and future vacuum anymore, but just only the 0s and 0n. And also further, if we chase over the southern modes, we again obtain the northern density matrix. And it's given by here, which now we only have the northern vacuums included. And it is weighted by a similar factor given by the exponential minus 2n and pi mu. So here, it is less obvious with the light scalar fields, where we can straightly identify it with the L0 operator. Instead, here we only have this the real part of it, or the imaginary part of it. But So although if we do a kind of trick, we can reproduce the L0 operator here. Because if we notice that, we notice this phi n operator, they are, so the explicit explanation, the definition is given by here. So it's constructed by this plus qn modes and minus qn star modes, and also minus aqn and this modes. So if we look at its eigenvalue of L0, so this first two terms are given by minus delta plus minus n, and the third and fourth terms are, their eigenvalues are given by delta minus plus n. Notice that because in this factor, in this exponential factor, it's actually times by a 2n pi. So if we just substitute like 2n pi times n, or the real part of this delta, which is 3/2, they will just give a minus here. Therefore, we have this relation where exponential to my 2 pi I L0 equals to just minus exponential minus 2 pi mu. Therefore, using this relation, we can again write this thermal weight part in terms of L0, and then further in terms of the static patch Hamiltonian. So therefore, we can eventually we can write the Norden's density matrix in terms of this form, which is given by exponential minus 2 pi h static. And so it is the same with the light scalar field case. Therefore, we can say that the thermal density metric and also the thermal field double statement also apply for heavy scalar fields. All those two are different, a little bit different derivation. So at the end, I will talk a little about the DSCFD or the dual boundary theory descriptions. So as similar with the light scalar field case, we also have a two boundary theory. So therefore, we are able to consider two dual with the CFD, which similarly we said it denote the first CFD as the using letters A, and also the second one with letter B. And also this kind of states are created by a kind of O operators here. And although one problem with heavy scalar field is that this operator O, they're supposed to deal with the boundary field, which is this phi n and phi s operator. However, those we have seen a little bit before, because these two operator, if we check its definition again, they are actually combined. They consist with fields with different conformal dimensions. So which means this operator deals to these two fields is a mixed form of DFT operators. So it's it cannot only be expressed by one single CFT operators. So that's the biggest difference between light scalar field and heavy scalar fields in terms of their dual CFT interpretation. Oh. But actually, this fact is consistent with the flat slides, the CFT description for heavy scalar fields, where so normally heavy scalar fields on the boundary is they oscillate on the boundary, so therefore they correspond to a mixed form of CFT operators, which is usually written by this, and this plus and minus are having the correspondingly delta plus and delta minus conformal operators. So this result seems consistent with this result. But although if you want to consider a similar DSCFT description with light scalar field, we still need a further investigation about how to interpret it, or how to interpret this would be CFT vacuum state or the entire theory. And also, I still haven't looked into it further yet, but I think Pachi mentioned that there might be also another construction or another interpretation that like each boundary theory, like the northern patch or the southern patch, each of them actually corresponds to each mode. There are also a possibility of that. So, so that's the result we have derived so far. But if we find a way to properly explain what this would be CFT means, it will complete our work. So basically, that's all of my talk. And let me give a brief summary of it. So basically, we studied the quasinormal modes mainly for heavy scalar fields in global coordinates as the basis for their safety. And then as a result, we showed that the Euclidean vacuum can be described as an entangled state of the northern and southern modes. And by tracing over the southern modes gives the expected northern thermal density matrix, which resembles the feature of a thermofield double state. And then we also find the boundary interpretation for the bulk theory, and the bulk field corresponds to a mixed form of CFT operators with different conformal dimensions, which kind of complicated the identification of the CFT. So which require further work or further investigations. And also there are a few comments about it. It's not really important, but just to mention it. So still quasinormal modes, it's very convenient for investigating the CFT, but it also has some unusual properties, such as having imaginary eigenvalues with respect to the static patch Hamiltonian. Also, so we still need some maybe we still need some further study of like why this property arises or what it means. Second is that it's just mentioned by Chongqing and Cottage works, and that this kind of due to global DS can also be described by two safeties which are coupled by a disordered average, and which is studied by some papers from a few years ago. So that's all. That's all of my talk. Thank you. So I'm not really familiar with that actually, but I think so these two papers, they suggest a kind of disordered average, which can be computed by the replica method. And also this is only applied for light scalar field as well. It's not really related to the Heaven one. Yes, sure. So actually, I think the thing yes, the temperature is imaginary.
Yeah, interpretation.
I don't think we have an interpretation now. It's just it's also the thing with that the Hamiltonian, the eigenvalue of the Hamiltonian is imaginary or complex. So I think that's one problem with the quasinormal modes too, and we don't have a proper explanation of it yet. Mm. Mm.
This is very
Oh, yes. Yeah. Mhm. Yeah, I think so. Yeah, I think it depends on like which boundary you choose. It's about what you said about lower. Oh, yeah, I think it doesn't really depends on the fields, but the non-empirical issues will apply or will appear. It's mainly because uh, um, it's not non-empirical on the procedure side, but oh, okay. Yeah, I think the non-empirical issue will appear as long as you will use quasinormal. Yes, yes, but it's important. Yeah. Ah, for example, if you are on self private license. Any more question or next? No need.
음. 你很好的心愿，我们好心中的事情，可是有啊，有吗？ 我少讲一点呗。那我共享屏幕
方面，
对不方便。
哦对了，
电影
你要不你看什么东西，要不就半小时吧，
少讲点吧。
分钟，那个什么的，然后就是
名字我差不会差差几个。
方法。
哦，
不行，根本不行。这边插口的这一边，可以。
没看到呀。不行。不行，这个没反应，要不还是换你的电脑吧。
我的电脑怎么了？
对，在这个投影仪投不上去啊。我看一下。
你要不然还是让用你吧。
我不接触了。
用一个实在是没有联系。然后等待了10分钟我来。就说让他们。
这是这个口怪了。
有一个口码，
这个一般只有一个。收到信号。好像确实差点没反应。那就换一个电脑。
很快，因为他可以上面说话。正好然后我们这个样。说法在还没有话。
在这里吗？
我微信发的。
哦，微信。
Okay, let's get started. Oh, we should. Let's get started. Good afternoon, everyone. My name is Zihao Wu, and I graduate from University of Science and Technology of China. And now I'm working as a postdoc in Hangzhou Institute of Advanced Study. Okay, today I'm talking about some new developments on the methodology of Feynman integral computation in fields of quantum field theory. My talk is based on the research references listed here. Okay, this is my table of contents. And in the first part, I will give a basic introduction of Feynman integrals. I will talk about what is a Feynman integral and why do we need Feynman integral and what difficulties we encounter in Feynman integral. And in the second part, I will talk detailedly about the mainstream Feynman integral computation method, which is called Feynman integral reduction. And we will show you what limitations we have in this kind of methods. And in the third part, I will give you a mathematical introduction of new methods we have introduced to solve the problems we mentioned in the second part. And in the fourth and the fifth part, I will introduce you the two packages we have developed using the methods we introduced in the previous sections. Okay. Finally, is the summary. Okay, let's talk about the introduction of Feynman integrals. We know that quantum field theory is a very important theory for nowadays, especially for high energy physics, including particle physics. So we know that the particle collision is a crucial experiment nowadays to study the properties of fundamental particles. And in the quantum field theory, this kind of particle collision is described by a physical quantity named the scattering amplitude, which is the inner product of incoming state. Here, I show you here is the two particles coming together, and the outgoing state, the final state, which is the pieces after the collision. Okay, this scattering amplitude, it's squared is the probability of such a reaction. Okay, in quantum field theory, we cannot directly compute the scattering amplitude. A typical way is to compute them by perturbative expansion, like I show you here. Each order corresponds to a bunch of Feynman integrals, Feynman diagrams I show you here. So this is an example of two electrons scattering and two electrons goes out. And I show you in the first order is the simplest reaction, which is the two electrons interchanges one virtual photon. And the second diagram is the next order, which is interchanging two virtual photons. And using Feynman rules coming from the Lagrangian of this the theory, we can translate the diagram to expressions. And if a diagram contains a loop here, we will have undetermined loop momenta here. So this kind of diagram corresponds to a integral of this kind of loop momenta, which we called a Feynman integral here. And so as I showed you before, scattering amplitude is a very important concept connecting quantum field theory and the experiments, and the loop Feynman integrals are one of the main methods of perturbatively computing them. And nowadays, as the experiments getting more and more precise for scattering amplitude computation, we need more precision to meet the precision of the experiments and also guiding the discovery of new physics. So that means we need to compute multi-loop Feynman integrals here. However, multi-loop Fermat integral computation is a very, very non-trivial task. I will show you later what difficult we encounter here. The mainstream Fermat integral computation methods is by Fermat integral reduction. What is a Fermat integral reduction? If you, given scattering amplitudes, you will have many Fermat diagrams, and they correspond to different kinds of Fermat integrals. However, not all of them, we don't need to compute all of them because they have some relations. We will, using those relations, we can reduce a lot of Fermat integrals to only a small number of integrals, to small number of intervals. And these kind of intervals are called master intervals, which is what we really need to compute. However, for high multi-loop Fermat integrals, these reduction steps are very complicated. Each steps are very complicated. In this talk, we only focus on the final step here. It's called integration by parts relation, which is to reduce such kind of scalar integrals to master integrals, and we will show what the difficulty are. So Fermat integration by parts reduction is kind of using the what you learn from calculus. The integration by parts gives the integration of a total derivative gives you a surface term, and the surface term vanishes. And using that knowledge, we induce a lot of linear constraints on different kinds of Fermat integrals. And by solving such of a system of linear equations, we will get our reduction result here. However, there are many difficulties. The first difficulty is that you know that solving a linear equation is like a Gaussian elimination over the coefficient matrix. However, this kind of matrix we encounter for a typical problem is very large sized. For example, we can have 10 million or so a matrix, and also this the entries of this matrix are multivariate functions. So it is important. It is impossible to use a common Gaussian elimination methods to directly reduce them in a tolerable time. So that is the first problem, that such kind of computation may cause us many days or weeks, even using a cluster. And the second problem is that even if we have finished our computation, these coefficients, the coefficient results we get are really huge sized. For example, we have encountered such examples that such kind of coefficients are up to 20 gigabytes written on the disk. So it is hardly usable for physicists. So as a consequence, we have two questions. The first question is how can we do to avoid the Gaussian elimination of such a large matrix? And the second question is, after the reduction, can we simplify the reduction coefficients? So keep in mind that the two questions. Today, my talk is mainly focusing on these two questions. Mm-hmm. Yeah. Two loops. Yeah. I would. It's irrelevant to theory. We only consider the scalar integrals. So it's only relevant to the topology of the Fermat diagram. Oh, it's not that scalar. I will show you later what a scalar means here. Okay.
Means that video complete it by hand
Yeah.
and see that's why it's a complete. We can
I think you cannot solve the 10 million matrix by hand, right?
For example, it's hard for me to understand how it feels when you're computing say fundamental force series with much less diagrams.
Okay, I see. So in some other theory, which I'm not so familiar with, we may need to compute integrals with higher numerator degrees. So they are very difficult.
So when do you have
I will have a lot of loop moment in the numerator of the integrand. So this kind of integrals are very, very hard to reduce.
I mean, you have to reduce scattering, but
We will encounter 2 to 3.
we are going to talk about scalar integral, which is in
Yes.
it's a even for the scalar integral.
Yes.
it becomes complicated when you have a lot of momentum and a lot of different momentum. Not like a box diagram, or
For example, box pentagon that in the numerator. In numerator. Yeah, for higher loop problems, we may have complicated numerators.
You must say, I point a
Yeah. So today I'm going to introduce the solution via algebraic geometry, which is the algebraic geometry itself is a theory that studies the algebraic curve or surface defined by polynomial equations. However, in this talk, we are only using some methods or concepts coming from this theory, like polynomial division or something else. And using such kind of concepts or methods, we will develop some algorithms to solve the two problems respectively. And we will see that the first algorithm will make us to generate a much smaller sized linear system and making us more capable to solve those equations. And the second algorithm is just a simplification of the IBP reduction coefficients. And we have developed 2 packages based on these 2 algorithms. Okay, so let's enter the second part of Fermat integral reduction. As we know that in general, Fermat integral coming from some kind of theory is written in this part, right? This is the integrand, and in the denominator there are some propagators, and you have a numerator with some tensor structures. Okay, so the first step of computation is just doing a tensor reduction here. So there are many kinds of tensor reduction methods, and I'm going to show the most classical way of doing so is Passero-Weltman reduction. So the basic concept is just to make an ansatz of this kind of to make an ansatz with undetermined coefficients, and by inner producting the allowed tensor assumptions, we will see that this kind of undetermined coefficients are some scalar integrals. And after some further mathematical analysis, we can see that this kind of scalar integrals can be expressed as such kind of standard scalar integrals, the combination of such kind of standard scalar integrals here. with the numerator equals to 1. So such kind of integrals here with arbitrary integral indices form a set. We call that an integral family. So what I mean by scalar integral is like here. So the benefits of doing so is that after this kind of reduction, what we are going to study is depends only on the topology of the Feynman diagram. For example, how the propagators are connected and whether one leg is massive or massless. But it is irrelevant to the theory itself. So irrelevant to the Feynman rules, no, the vertex. I don't care about that, right? So afterward, we are going to focus ourselves in how to compute such kind of scalar integrals. So such kind, the typical way of doing so is by a method called integration by parts reduction. Here is the integration by parts, or in short way, IBP relations. Is the integration over a total derivative. And in dimensional regularization, this surface term is 0 here. So you expand the right-hand side, you will get a linear combination of different kinds of scalar integrals here. So this is the IBP relation you get. And in fact, you will get many of them. So by solving this linear system or Gaussian elimination, you can reduce a given integral in this family to as a linear combination of master integrals, which are linearly independent bases. And also you get the coefficients of them. So this, okay. Yeah, it's not a constant. It can be chosen by loop momenta or combination of loop momenta or, yeah. Yes, given the V mu, you get a identity. So different V mu, you get different identities. Yeah. So this is the example I just mentioned, which is a 2-loop 5-point planar diagram. So we have this is an example of the traditional way of doing so. So we are reducing the degree 5 numerator target integrals, which means the numerator with power up to 5. So there are only 2,000 of them, and using the traditional packages like Fire 6, we tracked the equations they use. We find there are 10 million of them. So that means we need to do a Gaussian elimination of 10 million times 10 million matrix, and each matrix, the matrix entries are such kind of polynomials or rational functions. So you can have a try that it's impossible to do that even on a cluster. Yeah. I don't mean impossible. It's very hard. It's the time consuming is not tolerable. So it is the first problem. The second, yeah. Yes. The author is Semyonov. It's a Russian. Yeah. Yes.
So the reason of complication that you want to have a basis of the field temperature.
Yeah.
And you want to make it independent. So that's why. And if you want to compute field temperature with those, you have to basis value. But for example, a standard model people calculate with temperature.
Yeah.
But in this case, there is such a complication. But if you want to have a fundamental basis of the temperature, you have to solve this big problem.
The case is that in general, the computation of Feynman integral itself is very difficult. It's not, especially for higher loops, so you cannot directly use Feynman parameterization or something else. Yeah. Yeah. Not only the 9 spaces, but also the the integrals you want, the expansion coefficients on towards the basis. Yeah. So the coefficients are more important. Yeah. The basis you can, if you only want to find the basis, you will not need to reduce such degree 5 integrals. You can choose some degree 3. Maybe you can get the basis. That's more easy. But if we really need to degree 5 numerators, it's hard.
This package was used for example, UHC experiment because I got the scattering process.
Yeah.
And they also
I think so. There are many kinds of such kind of packages. Fire 6 is one of them, and there are also something like Kira, finite flow. There are many choices. We just pick one of them. Yeah, just to show the difficulty of such a problem. Yeah.
So degree 5 numerator corresponds to something like, for example, normal reaction.
I don't know exactly, but I think it's coming from some theory. Yeah, you're right. Coming from the power counting, or coming from the power counting condition. It corresponds to the specific theory. Yeah. Okay, so let's move on to the second problem here. After even if you have finished the reduction, you will see that the coefficients are really huge here, and this is an example of 2 5-point non-planar diagram, and also degree 5 targets. And after the reduction, we can see that the size of the results are 20 gigabytes. So it is not usable for next steps. So this is another problem we need to solve. Okay, so let's forget about the physics I just introduced. Let's come into mathematics of how do we. I will introduce some concepts in algebraic geometry. Okay, algebraic geometry is a theory that studies polynomials, which is a set of polynomial equations defines a surface or a curve in the coordinate spaces. I think maybe I need to skip this part, considering the time is limited. Maybe okay. So this part is some concepts of polynomial theories. I would like to skip this section because I don't have enough time.
Oh. Okay, and
Maybe.
What?
Well, if you continue this, if you have.
No.
Yeah.
Okay, you can 10 more minutes.
I started
20 more.
20.
Okay, 20 more.
Okay, that's enough. So this theory, so such kind of equations form a algebraic structure called ideal. That means if this equation holds, any combination of this kind of polynomials are also equals to 0, right? So these GIs are arbitrary polynomials. So such kind of polynomials form an ideal in the polynomial ring. By polynomial ring, I means all the polynomial considered, the set of all the polynomial considered here. So this is an example of an ideal, which, for example, I will say that an ideal is generated by only one polynomial x squared. So the ideal is all the polynomials with the linear term, with the linear term, and all the polynomials that's proportional to x squared. So such polynomial will have zero vanishing linear term and constant term. And this is the concept of ideal. And another important concept is the polynomial division. Like here, I have an ideal and I have a given arbitrary polynomial, and I want to write the polynomial in this form, which is the sum of an element in this ideal and a remainder part. And the remainder is just a linear function. This is the definition of a polynomial division, which is just what I just read. I'm not reading it here. So this is a very simple example of a single variable polynomial division with a single generator. So you can just do it by what you learned from primary school. It's very similar to the integer integer division with the remainders. However, what we are considering is the multivariate variable polynomials. So the only modification is just to introduce a polynomial ordering, because you need to set what is a higher ordered polynomial. So there are some choices, which lexicographic is that to compare the power of the first index, first variable first, and then the second. And there are many other choices here. Okay, so still we have a question about what if the ideal is generated by a set of polynomials? And this is a little bit subtle here, because if I just naively generalize what we have done in the single generator cases, you will find that this result is not so well defined. For example, I have an ideal here, and I have this method has already been developed about 10 years ago by David Causal. However, it is not so this is not optimized. We need
What did you do from the first line to the second?
the first line is
So original line.
the integration.
How did you obtain this bipolar representation?
It is just a variable transformation.
Okay. So your problem is not solving this, performing this integral, rather than you want to solve the relation. So this is simple. Okay.
Yes.
If you want to keep the switch to this through a
Okay,
computer,
switch a device. Okay.
yeah, switch device.
Okay. So I copy that.
哦，这啊，你换成这个呗。
This bipolar representation provides the same program.
Yes. So it is equal. It is equal to the order representation. Just a transformation.
它这里跟
我就拿过来了。
怎么接？它另配置。
那这个怎么整？这个
那这怎么接？哎，所以你这个怎么接？啊，直接。你这个怎么接那个荧幕？
还有我要屏幕共享吧？你现在是？
对。
你现在只是在看这个。
是。哦，它这已经共享了。
已经共享了。
对。那这个荧幕怎么接？
这个鼠标能接上？
这个我看新的。接头是，这个是，你这个接头在哪？应该是，
这不是一个吗？
是哈，
是。
它这个接，这个之前用过的，是这个吗？哦，是可以，
可以了啊。
可以。
但是这个不是，哦，我能把这个关掉。
可以。
能把鼠标接上吗？这能接鼠标不？
应该可以，应该是。鼠标怎么样？
哎，那个用这个那个，哎，这不是有吗？
对，鼠标怎么换页？
换页直接按哪？
按哪一个？按那个键，
对，
按下。
可能要指，可能要 point。
按下就行了。
好，没有就算，没有就算。好，
按下。
好的。
按下老鼠。
Okay, let's continue. And here is a backup representation here. And in the backup representation, we are also using integration by parts methods to generate such kind of relations here. However, after the expansion, you will see some abnormal terms here, and you will have here a. These a are some given polynomials, and this a must satisfy some equations to make this formula really an IBP relation. So this equation makes sure that this is an IBP relation, and this equation make sure that this kind of IBP relation are without multiple propagators. So after solving these two equations, we will get such kind of IBP relation without multiple propagators, which is exactly what we want. Okay, these two equations are called CCG equations. So you can see that the polynomial P here is called Bikov polynomial, which is the Jacobian identity of the variable transformation. And this is known here. And the derivative of this polynomial is also known. So they form a basis, and the A and B's are the CCG we need to solve. And this is also an CCG equation, but relatively simple. So we are using singular to solve these two equations. And after solving them, we can substitute back to the IBP relations. So this is the workflow of this algorithm. First, we need to derive the Bikov representations and solve the CCG equations, and using the equations to generate the IBP relations. And after generating, we are further selecting the independent ones and the really usable ones. And this part is developed to our package named Neat IBP, and this is already released on GitHub. You can find it using this link. The current version the current version has been renewed, so you can see that on the site. So the Neat IBP is very, very user friendly. So you need only to prepare your kinematics of your including propagators, your external momenta, something like that, and your target integrals together with some configurations. And you can only use in one command, and it will run automatically. And after that, it will give you the IBP relations you need and the master integrals. The second feature of Neat IBP is it is paralleled, and it uses a tail mask strategy to parallel between the sectors of Okay. Between different sectors of a Feynman integral family. So if you have a multi-core computer, this Neat IBP is good for you. Okay. So the parallelization method here is a framework based on a manager and different workers. So the sectors are with some kind of web structures here. So for example, here, the sector 3 and sector 4 needs to finish, and then sector 6 immediately starts. So it is different from what Fire or some other programs, they just parallel over a same layer, but this Neat IBP is different. So it parallel over all the webs. So I will show you the outcome of Neat IBP. So I need to clarify that Neat IBP does not solve the system. It just generates a small system for you, and you need to use your own codes to solve the system by yourself. And for the same problem I showed you, we need 10 million equations. However, Neat IBP only gives you 10,000. So it's around 1,000th decrease of the size. So it is so if you consider the direct Gaussian elimination, which is N3, you can expect 10 to the power of 9 9 improvements of this. So you can find this example here. Okay, these are more examples. I will skip. The final part is okay. The first, the final part is to solve the second question. After the reduction, we will have a large-sized coefficients. For example, here is what I just showed you, the 20 gigabyte ones. We are going to simplify this. So these coefficients are all fraction functions, usually rational functions, at most with some square roots. So using that property, we're going to simplify. Sorry, this is an example from the 20 gigabytes file, and it's 5 pages long. And after magnified, you can see that only the last 2 lines are the denominators, and all the rest parts are numerators. So this is very typical. This is a very typical structure we have discovered, because if you have a lot of very simple fractions, multivariable fractions adding together after you write them to a common denominator, the result are with a very simple denominator but a very large, huge numerator. So the reversed operation is called partial fraction decomposition, and using that we're going to using that to simplify our fraction in this kind of type. So the univariate partial fraction decomposition is a very developed problem, and even in Mathematica even in Mathematica there is a command named apart. You can do that. But however, the multivariate partial fraction decomposition is non-trivial. You cannot just using this kind of apart command to if you can see, I can act on the first variable and then on the second variable. That does not work. And you can see that in the final part here, I act on x1 and then act on x5. The results are very the same for directly given x1. So this mathematical command is in principle not a multivariate partial fraction decomposition method. So we need more algorithms, and that algorithm is called a Linatas algorithm. It is developed by Linatas. It's also a Russian researcher. The Linatas algorithm are using 2 methods coming from algebraic geometry. One is the decomposition where Hilbert's non-stereogens, which means that first you factorize the denominator, and then you can see that if the denominators have a common zero point, if not, the Hilbert's non-stereogens theorem tells us there is a combination of them that makes the combination equal to 1. So using that, under this combination coefficients, which are polynomials, which are solvable using using the singular program. Okay, so if you have that relation, you can see that this is my original expression, and you can multiply by 1, which is this kind of combination, and after expansion and canceling, you can see that each fraction are with less number of denominator factors. So it's just one simplification, and the second simplification is similar, is to find some algebraic dependency between the denominators, and if you find them, you can also get a 1 equals to some expression, and you multiply by 1, you can similarly simplify the original expression. And our modification is to add some new types of methods into that algorithm. This is by polynomial division, which is just to divide the numerator by the denominator factors, and still similarly we can after substituting this relation here to the original expression, we will get a summation of simpler fractions. So let's skip this. The final workflow of our algorithm is that the white part is original Linatas algorithm, and we have added 2 steps into them. We call that improved Linatas algorithm. And using that algorithm to that example I just show you here, you can see that this fraction is simplified to a lot of much simpler small fractions. Okay, so this kind of algorithm has been developed to our new package called Ph.D parallel. Also on GitHub, you can download it, and if you need, you can try it. So the features are also this is also a parallel package. Okay, and using that package, we can see that these 20 gigabytes results are compressed to only 200 megabytes. It's just like you compress a book to only a small pieces of papers. And this is a very the example. The 5-page results using our package only half pages long. So, okay, so let me summarize my talk. In quantum field theory, Fermat integral computation are very crucial for high energy physics, and the mainstream methods of computing Fermat integrals is Fermat integral reduction, and it always serves as a bottleneck.
Yes, thank you for your talk. And the next speaker is Chongman So from Tsinghua. Could you share your screen, please? Hello?
Okay, yeah. Can you hear
Thank
me?
you. Yes.
Okay, here I just share the screen. Okay, can you see the screen here?
Yes.
Okay. Then so shall we start now?
Yes.
Okay. So thank you for inviting me to give a talk in here. So today the title of my talk is about the coherence of cosmological perturbations. And this talk is based on my two recent works published on JHAP, and you can also see the archive numbers if you are interested in. So first of all, I want to give some very basic background and the motivations of why do we care about the coherence of cosmological perturbations. So in case some of the audience are not working on cosmology here, we just start from a very basic thing. So for example, do we solve the fatness problem, the horizon problem, and etc. So the leading paradigm to describe the primordial universe, of course, is the invasion. So in the invasion theory, it suggests that the early universe have experienced exponential expansions. For example, we can describe such a geometry with the FRW metric in the form like this, and with a scale factor A. And this scale factor will grows exponentially. So, and also you can see the figure in here is like if you define the time slice of this universe, you will see that, for example, you put a volume and put a length in here, it will grow as the exponential factor, scale factor in here, for example, the power of e to the power of v and linear respectively. So it's also interesting if we focus on the dynamics of this kind of snowball, this kind of invasions. So it's so-called the snowball invasions. So this simplest model, we all we need is to introduce a real scalar field called the inphaton. And for such an inphaton, is required to have potentials have the shape like this to support such a inphaton field to have a slowly rolling down from, for example, the top in here and slowly roll down to the bottom of the potentials. And from such a potential, we can calculate the Hubble parameter of how fast the universe expands. And we will see that it's really a constant. However, if we study it carefully with the equation of motions, we will see that this Hubble parameter will change slowly. And we can also introduce two parameters, which is called slow-mo parameters, epsilon and eta. Both of them are constraints observationally. And so for the rest of my talk, we are only focusing on such a simplest model, an inflationary model, and all we need is these two parameters to mix all the computations. For example, estimate how large is the size of the decoherence effect, and also identify which part is important for the decoherence problem. And just remember, so for all of my talk is about the simplest inflation model and no other ingredients. So for such a background, we can also expect that because the infiniton can introduce quantum fluctuations, and also gravity itself can also have a quantum degree of freedom, and we will expect that it will generate, for example, the scalar curvature perturbations and the tensor perturbations. So if we express this in the metric, it appears in the spatial part, Hij in here. So here I follow the medicinal conventions. For example, it's really convenient to do all the non-Gaussian computations. And also, you will see that for such a conventions, we express the scalar and the tensor perturbations degree of freedom with the exponential form. It's because it has several advantages. For example, it will conserve, for example, outside the horizon scale and etc. And it will keep our result more easier to understand for the late-time evolutions. And therefore, we choose such a variables. And then for such a primordial perturbations, so the origin is actually from the quantum perturbations from the vacuums. For example, if we start from a vacuum state with the wavelength much smaller than the Hubble horizon size in here, so because the wavelength will grow exponentially, as I explained before, and such a perturbations will be grows and until it reaches the horizon's size in here, and then it becomes a super horizon scale like this. And for this kind of process, it will keep growing until the end of invasions. Then after the end of invasions, such a Hubble horizon will grow, and eventually all the perturbations which grow outside the horizon will go back again, and then it become returning the horizons. It becomes all the observations, cosmological observations that we can observe today. For example, if we start from a CMB observations in here, we will see that the power spectrum of how we measure the CMB power spectrum is actually have a quantum origins starting from the very beginning in here during the invasion. Then, as I explained, so all of these kind of perturbations have a quantum origins, then we are better to look at what kind of quantum state that they will evolve during the invasions. So we can just use the simple canonical quantizations of the perturbations. For example, for the scalar, we expand it with the mole functions and with the annihilation operator, inclusion operators, and gravitons also expanded similarly. So it's interesting that if we use the A and A dagger in here, for example, for the scalar phi Hamiltonian, we can express this in the following form. And this is well known in the 1990s. It's like the Hamiltonians have this forms like, besides the harmonic oscillator form, it also have a time-dependent term, which is describing the squeezing process. So it will generally turns the vacuum, initial vacuum to a two-mode squeeze state. And it's very interesting to look at the form in here. If you look at the expansion in the power lumbar eigenstate, you will see that the particle lumbar eigenstate with the directions k and the minus k will entangle together if the squeezing parameter described in here is RK is not equal to 0. And this kind of property is very crucial if we want to try to probe the quantum origins of such a perturbations. So for the following discussions to be more convenient, we are better to look at the wave functional. If we represent the state in the basis, for example, the field basis, we will see that for the free field getting any interactions, we will expect that the quantum state is a Gaussian state. And all the Fourier modes labeled with K here will evolve independently. And this wave functional is expressed in the eigenstates of the field operator divided in here. And the subtleties, you can see, for example, the modes of the opposite directions, for example, K and minus K, they will mix together. But this point can be easily seen if we define another set of bases. For example, as I explained before, if we do a canonical quantizations for the field operator is divided with the A and A dagger with two different directions. However, you can also define another set of operator called a Q. In the literature, someone will call position operator because it's quite similar to the positions in the simple harmonic oscillator in quantum mechanics. And it is all divided with the same directions K in here. And by doing so, we can we express the wave functional in the Liu basis, and you will see that if the squeezing parameter is non-zero, you will see that the wave functional cannot be separated into directions K and the mass K in here. And therefore, it's very clear to see that the two modes will entangle with each other. And also, I would like to talk about some facts about this kind of two-mode squeeze state. So for the squeeze, of course, the most important point is the squeezing effect. And this is measured by the squeezing parameter that I just defined. Then how large is this during the invasions? We can do a simple calculation to show that such a squeezing parameter is actually proportional to the e-folding numbers after the modes crossing the horizons. So the e-folds here means after the horizon crossing, the universe will expand exponential to the power of n times here. So for the invasions, we all know that, so it lasts for at least 50 to 60 e-folds. Then I will expect that the squeezing parameter can reach, for example, 16 in here. If we change this into the unit of decibel, we will see that it's around 260. Then how large is this number? We can compare it with the squeeze data produced by human in lab is around 20 decibel. And you will see that the squeeze state produced during the invasion is actually much stronger than the squeeze state produced by human. And how to utilize this fact, the entanglement accompanied with the squeezing, if of course is to construct some quantum information test. So here is the first attempt. For example, some groups of authors have already been constructing the Bell test for the cosmology. It relies on constructing a set of so-called pseudo-spins operator. So for the standard Bell in a spell test, of course, we are measuring the physical spins. But for example, for the scalar degree of freedom, there's no spin, then we should construct some operator which has a property is similar to the physical spin. Here, the diagram I show in here is like the logic of how this kind of measurement happens. So as I mentioned before, invasion is like a source of producing the entanglement states, of which entangling the K and the minus K directions. And of course, we should define some operator which can extract the discretized eigenvalue in the K directions and in the minus K directions. So here is one kind of suggestions of how to construct such a operator with the eigen states divided by Q in here. So this set of pseudo-spins operator will satisfy the algebra that what we need for constructing the Bell inequality. For example, the commutator is the familiar form for the spin operators. And by using such a pseudo-spins operator, we can construct a Bell inequality to test the quantum correlation between the two modes, k and minus k. And if it violates, of course, it can be used to prove that the cosmological perturbations is indeed have a quantum origin. However, there are some obstructions of such a cosmological Bell test. One is the measurement aspect. It's because it's very difficult to measure the non-commuting operators, what I just present and be quiet. For example, for the CMB observations, what we are observing is eventually can be converted to the field operator. However, if we want to construct some non-commuting operators, we should also measure the conjugate momentums of the field, which is this one. However, it's very difficult to in the reality to measure it in the cosmological observations. And another aspect is really related to the quantum state for the perturbations. So one aspect is, of course, the decoherence. So the decoherence happens when the observed parts of the quantum system is interacting with the environment, which is the part that we are not observing with. It can generally destroy the variations of the Bell inequality, as you can see in this figure in here. So if we don't have any decoherence effect, of course, the variations of the Bell inequality can happen. For example, it's greater than 2. However, if we generally increase the effect of the decoherence, the variations of the Bell inequality will drop and eventually drop lower than the critical value 2. And therefore, this aspect will motivate us. At least we will try to quantify how large is this effect compared to the measurement aspect here, because the measurement aspect is very hard to tell whether we can really find a way to test the non-commuting operator. However, in the current framework, that what we can do is really to analyze how large is this decoherence effect from the simplest model of invasion. And this and other type of experiments proposed by the authors in here is try to probe the quantum origins of gravitons. And it turns out that this kind of setup can also be used to probe the primordial gravitons produced during invasions. So the idea of their setup is like, so when the gravitons with the quantum state, some quantum state is passing through the gravitation arms. So together with the classical effect, for example, the distort of the detector arms labeled with the blue graph in here, along with this, the red random path where it represents the quantum noise produced by the quantum states of the graviton. It can be estimated. And if such a quantum noise is measured, then what is the important point? The important point is that it can somehow be proved, be used to prove the quantum origins of the gravity. And we shall also take a closer look of how this happens. So this happens when we analyze the process is like incoming gravitons in the state of preside, and then interacting with the detector arms, and finally it becomes a final state which is not measured. Then we should calculate the probability of the detector transform from the state A to the state B. Then it can be expressed by the path integral in the Schwinger-Keldysh type. And this kind of path integral will have the form like with the action difference of two detectors configurations, and also with the key component is called the Feynman Whelan inference functional with the form like this. As you can see in the expressions of such an F, you can see that such a terms will depend on the state of the incoming gravitons. And we can also express the form of the Feynman Whelan inference functional into a functional integral form, which is expressed in this one. And this done by introducing a auxiliary field n in here to mix the terms related to the detector arms configurations to be the form of the action difference. And if we insert this part back into the probability form in here, you will see that this part will eventually contribute a noise term in the EOM that I just showed with you. And this is also interesting to look at how large is this noise term n in here. This is characterized by the octocorrelation functions written in here. And we will show that this kind of octocorrelation functions will be enhanced exponentially by this squeezing parameter out here. So we can also estimate how large is this octocorrelation functions by doing a Fourier transform. It becomes a power spectrum. So some estimation have already been done in the literature. Is the power spectrum, how large is it? If we compare with the, for example, the vacuum state of the graviton, of course, this power spectrum is very, very small. And it generally requires the positions of the detector to reach the Planck's length. And of course, it's not feasible for us to detect it. However, if we estimate for the squeeze state, you will have exponentially enhanced by the squeezing parameter. And then other group of authors also estimate how large is this effect compared with the effective strength of the gravitational wave detector, like the next generation one. And it's possible to reach the sensitivity of the next generation detector in the near future. And if the squeezing parameter can reach the value of around 42, then as I just shown before, the squeezing parameter produced during the invasions can generally grow with the E-folding number. Then of course it's possible during the invasions. Then this one key point for the current proposal is like it does not consider any decoherence effect during the invasions, and therefore we will see that this kind of proposal can maybe affected by the decoherence happens during the invasions just for the simplest invasions model. And we want to explore about this. So here I just want to summarize the motivations that I have discussed so far. So one point is that so the cosmic decoherence problem have already been studied for many years, but many works only focus on explaining the quantum to classical transitions, but not quantifying how large is this effect. However, this problem turns out to be very important when we want to exploit with the recent proposals of popping the quantum origins. Then therefore, the quantifying the decoherence is now necessary to set up some constraints to the proposals. So here is the outline of the rest of my part of my work of my talk includes all the content in my works. So first of all, the first part I want to present is to discuss a little bit about the subtleties of expanding the gravitational actions perturbatively for the simplest single field invasions. So here we will focus on the boundary terms, which is the total time derivative form, which is usually neglected in the literature. And other parts, the second part is talking about the decoherence caused by this kind of boundary term. So the boundary terms I written in here are two examples. So one is about the scalar, one is written in here, and one is about the interactions between the scalar and graviton is also written in here. And we will show that such a boundary term will cause a non-Gaussian phase of the wave functional, and it will also lead to a much faster, which is slower, unsurpassed decoherence effect. And for the last part, besides doing the computations for the primordial gravitons, I will also like to talk about how to understand this kind of boundary term phase. I will provide another point of view to look at it is by the WKB approximations of the Wheeler-DeWitt equation. So here we start from the first part. So if we want to start the decoherence process for the observed part of the perturbation of the cosmological perturbations, for example, I label it with the Gaussian here. So this part of the perturbations actually forms an open system that I present with a set diagram with a shadow circle in here. It will also interact with other parts of the perturbation modes. which is unobserved, and we will call it environment. I label it with the E cursive E in here. So, for example, how to understand these kind of separations? For example, we can go to like the CMB experiment. So the observed range of the CMB experiment is actually range from, for example, 10 to the minus 4 to 10 to the minus 1 megapascal inverse. Then beyond this part is, of course, the unobserved part. Then it will form an environment. And we can also look at the form of the coupling. If we want to study this kind of system to an environment coupling, it actually starts from cubic interactions. So we can look at the quadratic first. Quadratic interactions will only interact with the mode with the same magnitude of the wave number. Then, of course, it can only be system-to-system interaction and the environment-to-environment interactions. However, if we want to have a system-to-environment coupling, then we should start from the cubic interactions, which is possible. Like shown in the graph in here is like the red one is with the observed range of the perturbations, and it will couple with two blue balls which outside the observed range of the perturbations. And it's also satisfied with the momentum conservations, which is the P1 plus P2 plus P3 is equal to 0. Then we go back to the very standard derivations from the famous paper by Madison. It's talking about the non-Gaussianity, how we derive the cubic interactions. So we start from a simple single field equations is written in here. And here I just want to have one highlight is the last term in here is about the Gibbon-Shocking-York boundary term. For making the gravitational theory to be well-defined, to have a well-defined variation in principle, we should also add this term. Then what happens in the standard literature is actually implicitly include this term. For example, when we do the ADM compositions for the richest scalar in here, you will also include some terms of the covariant derivative, but most of the people will just directly drop it out. Then by dropping it out, it's actually equivalent to adding these boundary terms in here. And here is just a short remark of this. And as discussed in this paper, you will see that it requires a very complicated procedures to how to divide the cubic interactions properly. For example, the correct non-Gaussian correlations like the cubic correlations in here cannot be directly calculated by simply expanding the equations in here. However, we will require some integration by parts, and we arrange with the EOM to select some above interactions are written in here to have a correct slow order. For example, for the cubic order, we can make the actions to expand predominantly and be arranged in the form like this. For example, the first group is about the bulk interactions that we usually use it to compute the non-Gaussianity. And for the second one is about the terms of the proportional to equation of motions here. And it will not contribute to any correlator, because if we go to an interaction picture and insert it back the interaction picture field, then it will be 0. And for the last part that usually neglected by many people is about the boundary terms in here in the form of the total time derivative written in here. So of course, it's very hard to calculate by hands, but we can also use our mathematical package. For example, MathGR work written by Professor Yi Wang to make this difficult task. So as I mentioned before, it will be separated into 3 kind of terms. So as you can see, for the bulk terms, is usually have a slow surpass for the terms related to the scalar perturbations. And for the standard calculations of cosmological correlations, correlators, we will usually focus on this kind of terms in here. And this one thing that we should also pay attention to is for the cubic terms, it depends on only the primordial gravitons, which will be slower and surpassed. And here is the EOM term, but we won't pay attention to that because it won't contribute anything. Then for the boundary terms, perhaps is the main role that we want to talk about during the presentations. So the boundary terms are often neglected in the literature, except for those one I highlighted with the red box. Around 10 years ago, some people have discussed the effects of this kind of boundary terms, which is related to the time derivative of the field. And it turns out that such a boundary term is related to the field with definition process. For example, if we do a field with definitions correspondingly, it can be shown that this kind of boundary term can be cancelled. And therefore, you can understand it's like by including this kind of boundary term is equivalent to doing the field with definitions of the perturbations. And for the remaining boundary terms, it haven't been explored so far. So this kind of boundary term will be the which is not highlighted in the red box, will be the main things I want to talk about. It's actually one kind of aspect of such a boundary term have already been discussed a little bit in the Madison paper, when he discussed like in the long wavelength limit, when the wavelength is much larger than the Hilbert horizons, then what is the form of the Lagrangians? He shows that the Lagrangians should have a total derivative form with the form like this -2h times some exponential factor. So it's proved used to prove the conserved property of the scalar perturbations in his paper. We can also study it carefully, then how this kind of term will contribute to the correlators. For example, we can check it with the Indian formalism. It actually won't contribute to any correlator in the form like this. Here, I just also write down if the wave functional aspect of how to calculate this one is actually related to the absolute value of the wave functional. However, if we go to study the contributions to the conjugate momentum, we will see that this kind of boundary term will actually be contributing to the conjugate momentum in the form like this. Then together with these 2 points, then we can do a conclusion slide is related to the phase of the wave functional. So it's because if we decompose the wave functional into the form of a relative and with the pure phase written in here, you will see that the left-hand side won't contribute to anything. However, the right-hand side, if we take a derivative, it will contribute to some you have some contributions. Then of course, all of the things contribute to the wave functional will be in the phase part. And I will verify this and show that it will affect the decoherence in the next section. And here we should take a rough look about what have been what we can see for the characterized for the categories of the Buck and the boundary interactions. For example, we can separate into different kinds of the interactions. For example, 3 scalar, 2 scalar, and 1 tensor, and 1 scalar, 2 tensor, and etc. 3 tensor. And we can study the leading interactions of each type. Then how large is this? I will use these relations. For example, the path spectrum of the scalar is slow larger than the of the scalar is slow relatively larger than the tensor power spectrum. And we can use this to estimate how large is this interactions term in here. And we will see that the boundary terms generally will contribute a less Lobel suppressed order, as you can see in here. For example, the leading term will be not Lobel suppressed, and for the 2 scalar and 1 tensor interactions, it will be of the order of square root of epsilon is greater than the corresponding type in the Buck. And also we can also look at the one scalar and 2 tensors interactions is epsilon suppressed is also larger than the corresponding type in the Buck. Then we can also take a rough look about what have been done in the literatures about the estimations of the decoherence effect. For example, here I just summarize some works done in here. It's like, for example, this for this scalar to be the system and for the scalar to be the environment. And for using the bulk interactions in here, it estimates is around 10 to the 15 eVolts to make the decoherence happen. And also, we can also see that, for example, for the tensor environment to decohere the scalar system, and for this tensor system decohere with the scalar environments also have also been computed, and the results are written in here. And what we want to do is to try to improve such estimations of the decoherence effect by including the boundary terms that we have just discussed and usually regarded in the literature. And here we go to the second part, is about the decoherence effect. So here I just have a rough introductions of what kind of methods we use to calculate the decoherence problem. So for computing the decoherence problem, the most popular ones have two types. For example, one is about the predictive method, and another one is about the Markovian approximations. This is because for the system states described by the reduced density matrix is not exactly solvable, and therefore we should correspondingly make some estimations to estimate it. So for the predictive method, so one kind of direction is to calculate the corresponding Feynman-Verlan inference functional by the Schwinger-Keldysh path integral in an open system. This has been done in the 1990s. And another aspect is to try to approximate the Schrödinger wave functional in the Schrödinger picture, and then doing the tracing out process to study the reduced density matrix. So this method have been introduced by Nelson in 2016 and is used in our works because as I will show that this kind of approach will have a very clear and easier look of how the boundary terms will contribute to the quantum states. And another kind of approximation is to approximating the equation of motions, the evolution equations of the reduced density matrix used to describe the open system. So it relies on assumptions like the relaxation time of the environment is much shorter than the time scale of the system evolutions. So this kind of method have also been used to compute the decoherence problem. So here I just have a schematic discussions of how the phase and what I just discussed is related to the decoherence problem inside the reduced density matrix. For example, if we want to describe a full density matrix consisting with the system state in here and also with the environment mode in here, it have the form like this. So if we write down into a matrix form, we will see that for the diagonal terms, it always depends only on the probability distributions like the P in here. However, for the off-diagonal terms, we will generally evolve the quantum interference with the phase difference in the form like this. Then the decoherence is categorized by the decaying of the off-diagonal components. So, and also we can understand that it's like the loss of the quantum interference will reach to the classical distributions. It's like if there's no off-diagonal terms in the density matrix, then all the things can be described by the probability distributions inside the diagonal entries in here. Then it's exactly a classical system. Then we can take a closer look of how the dynamics can render such a decoherence happen. Then it happens when the environment degree of freedom are tracing out. You can understand it's like taking the average of the off-diagonal terms in here with the taking the average with respect to the environment degree of freedom. So, for example, if we have a cubic interactions, what I have just discussed, the wave functional will generally have the form like this. Then this property is quite important. It's like this kind of cubic terms in the the cubic part in the wave functional will have the properties like the real part will converge to a value, but the imaginary part, which is the phase part, will grow with the scale factor at the late time. And therefore, if we look at the average of the tracing out process to derive the reduced density matrix, so you will evolve a integral with the form like this. For example, you have a Gaussian envelope and with a highly oscillating cubic phase in here. For example, if the two field configurations, Cassi and Cassi theta, is large, then it will have a very rapid oscillations. And if the field configuration difference is small, then it means close to the diagonal part of the density matrix, then you have a slower oscillations, and therefore we expect that you will have a suppressions proportional to the growth with the distance of the two field configurations. And it can be expressed in the forms like exponential minus the strength of the interactions and with the distance of the two field configurations. And therefore, from this reasoning, you will see that the non-Gaussian phase is very important for us to derive the decoherence effect. And here we go to the calculations of how this boundary term written in here will contribute to the decoherence effect. So one approach is to study the evolution operator at the cubic order caused by this boundary term. And for example, it will contribute to a Hamiltonian with the form like this with a total time derivative. And we can prove that the evolution operator will have a form like a exponential factor and times a free theory 1. And therefore, if we operate into the state to derive the evolutions, and finally derive the wave function, we will see that it will contribute to a phase factor in front of the Gaussian wave function. And therefore, it will introduce a non-Gaussian phase factor in the wave function. It's generally expressed in this one. And then we will compute the decoherence factor, which is a suppression factor of the off-diagonal part of the reduced density matrix. It's done by separating the environment and the system degree of freedom by identifying what is the correct Fourier modes that we can observe during the observations, cosmological observations. And then we can compute the corresponding suppressions is like to compute the expectation value of the phase difference of the off-diagonal terms, that it can be expressed like this. And since the interactions is in the cubic form, the leading order of such an expectation value can be expressed by one loop diagram written in here. And therefore, what we need to do is to try to compute this one loop diagram written in here is like for the bright line in here is the system mode with the wave number q, and for the red lines in here are those environment modes that we cannot observe and we need to tracing out. Then for the final answer, we can use a exponential decoherence exponent to characterize how large is this kind of suppression. And here is the result of such a decoherence exponent. So if we use the boundary terms to do the computations, we will see that the decoherence exponent has the form like this. Is inversely proportional to the epsilon square, which is, of course, is more than slow and suppressed. However, if we compare with the previous result done with the bulk term, then we will see that the result is actually slow suppressed. And by comparing these two, we will see that the decoherence is much larger if we include the boundary term effect in here. So here the two figure is to describe how large is the decoherence exponent growth after the crossing the horizon. Here the horizontal axis is to label how many evos after the horizon crossing. And here the red dashed line, I use the value 1 in here to represent around which point the state will be decoherent. And you will see that for the boundary term contributions is go much faster than the bulk interaction. And here we go to the last part of my talk is about doing the computations for the gravitons, and also want to have another point of view to look at this kind of boundary term phase. So what we have just analyzed is based on the integration by parts procedure, and also insert some UM terms to do the rearrangements of how we get the cubic interactions. Then, of course, we can ask a question like there are infinitely many ways to do the integration by parts to the actions. Then how can we ensure that we get a correct phase factor in the wave function? And therefore, one of my goals in my paper is to finding a method which is independent to the IBP. So here we should look at the generic form of the wave functional in the long wavelength limit. And it turns out that this fact have already been discussed by Pimento in around 2013. So the wave functional, when we go to the large wavelength, long wavelength limit, it have the form like this. So it can decompose in two parts. So one is about a phase factor, which is related to a real local actions written in here. And another part I will call it C. And this part will include some non-local terms. So one interesting fact is, as I mentioned before, when I introduced to the Nelson, the general property discussed in the Nelson paper is like the phase, the imaginary part of the wave function, which is the phase, is usually grows with the scale factor. However, for the non-local part, which is usually a real part of the wave functional, is actually converges at the late time, and therefore you will see that the phase will be a dominant component in the wave functional. However, when we go to estimations of the usual cosmological correlators, it's like the operator divided only by the spatial metric Hij in here. It won't contribute anything but from the phase factor in here. It will only contribute by the C written in here. It can be expressed clearly if we write down into the wave functional representations. It's like it always depends only on the absolute value square, and therefore you can see in here. And here I just give an example. For example, when we look at the three wave functional of the scalar perturbations at the long wavelength limit, you will see that it can be decomposed into two terms. So one, the real part is the k to the power of 3, which is included into the C I defined here. And another part is about the imaginary part, is growth with A and also proportional to the AK square in here. So these terms can be written proportional to the three-dimensional, which is scalar written in here. It will be included into the W phase written in here. And it turns out when we compute the power spectrum of the scalar field, you will see that only the blue terms written in here will contribute to the power spectrum. So it's proportional to the inverse of the coefficients in here. And here we can do some short reasoning is, so as I explained that it turns out that the wave functional is dominated by a phase. Then what's the meaning of the wave functional? Then we can study that is in the long wavelength limit. Then in such a limit, the quantum state will behave like a WKB form. Then it's close to a semi-classical limit. Then we will ask then what is the corresponding classical theory? And as I mentioned before, all we study is actually the Einstein Hilbert actions and plus the single field invasion, single field inverton potential Lagrangians. And therefore, of course, this classical theory will correspond to the classical general relativity. And then what does the phase mean in the GR is actually the Hamilton-Jacobi functional of the GR. Then what kind of quantum theory is actually approximating with the XJ functional in here is actually the Wheeler-DeWitt equation. Then the Wheeler-DeWitt equations of quantum gravity is generally difficult to solve. However, if we go to the WKB limit, for example, you can use an H bar to indicate then which order is the quantum corrections. Then we can extract the leading order. Then the solutions is actually the Hamilton-Jacobi equations of GR. Then it can be solved and actually be presented in the 1990s by these authors. We can see that the W functions, the local phase, is actually can be actually expressed into the form like this, and we can solve it order by order. And we will see that at the leading order of slow unsuppressed term, we will see that one part is about -2h is the term that I just presented, for example, from the Madison discussions of how the scalar perturbation conserve outside horizons. And also another part is proportional to the three-dimensional, which is scalar. And this part will contribute terms related to the tensor perturbations. And we can express it with the variables of theta and gamma. And here we can extract that all the terms appearing in here will just collect all the slow unsuppressed boundary terms, what I just divide with the mathematical package. And also with some terms, which is slow suppressed for phi tensor modes is actually come from the Buck interactions for the phi tensor Buck interactions. And this kind of method is independent to any integration by part and actually is not needed. And therefore, we can get an alternative method to confirm that our computations can make some sense. And therefore, we can repeat essentially repeating all the steps that we use to compute the scalar field, scalar perturbations, decoherence. Then we can just use it to compute the gravitons. So here, what we just modify is that, for example, if we choose the system to be a graviton with wave number q in here, then there are three kinds of possibilities if we study the possible environments. So one is by two scalar environments modes in here, and one is by one scalar environment mode and one tensor environment mode in here. And also both of the environment modes are tensors. And we can do the estimations of the decoherence exponents. For example, for the first diagram in here, we can express that the result is inversely proportional to the slow parameter in here. And also for the next diagram is actually no not slow suppressed and no slow parameter dependence. And for the last one is suppressed by the slow parameter. And we can compare this with the previous results done with the Buck interactions. Then we can see that generically for the Buck interactions will contribute to the same order of magnitude. It will be slow suppressed. Then, however, compared to the boundary term, we immediately can conclude that the boundary term will contribute the dominant effect to the decoherence. So we can also take a closer look if we draw figures like the previous one for the scalar. So we can draw how the decoherence exponent grow after the horizon crossing. We will see that. So in both of the situations, so the dominant ones will always be the boundary interactions. For example, the blue line in here is the two scalar environment modes, and here the tensor perturbations in here. And therefore, we will see that indeed the boundary terms will dominate the decoherence effect, and it have a very good explanation. It can be comes from the WKB approximations of the wave function of the universe. So here is my summary of my talk. So as I just presented during the motivation slide, quantifying a cosmic decoherence is very essential if we want to study some proposals of how to pop the quantum natures of cosmological perturbations, either by cosmological backtests or by the quantum noise in the gravitational wave detectors. So it's very essential for us to estimate how large is the decoherence effect. It can be reflected into the modifications of the quantum state itself. And another point is that what we have just studied is for the boundary terms in the cosmological perturbation theory. So these terms actually exist in the actions. However, it's usually neglected in the literature. However, as I have just shown, this kind of boundary terms can contribute much faster decoherence effect if we tracing out the unobserved degree of freedom, and it can improve the decoherence calculations for both the scalar perturbations and for the primordial gravitons. And for the last point, what I just gave is this kind of boundary terms effect can also be systematically analyzed with the WKB approximations of the Miller-DeWitt equations. And that's all my talk. Yes, any questions?
Sorry, can I ask? Sorry if I missed, but practically, can you how to say observe the how to say entanglement of primordial gravitational wave?
So entanglement, I guess. So the logic, if we want to estimate the entanglement, the best way, of course, is by the backtest. But the difficulty of the backtest, I think, is how to construct the spin operator is a problem. How to realize practically, then I don't think at the moment we have a very good way to how to realize how to evaluate the Bell operator from the observational data. And therefore, I would say if we focus on the entanglement aspect, then perhaps currently there's no good way to do it. However, if we want to pop the squeezing effect of the gravitons, then perhaps we can, I think the quantum noise proposal is a doable one. At least we can realize it into the gravitational wave detector.
Okay, I see. Thanks.
If there are no questions, we can end this session.
So let's end this session.